Welcome to Sleepy Science Hub. I'm so glad you've joined me tonight for this gentle journey into one of Earth's most peaceful and persistent mysteries, the vast networks of underground rivers and hidden waterways that flow silently beneath our feet, carrying water through ancient pathways that connect every raindrop to every spring, every mountain to every valley, in a slow circulation that has been flowing for millions of years with the patience and persistence that characterizes all of nature's most fundamental processes. As you settle in, let me know where in the world and at what time you're watching. Whether you're resting comfortably as evening settles around you, or perhaps finding a quiet moment in the early hours when the world feels still and peaceful, you've discovered the perfect time to explore the hidden world that lies just beneath the surface of our everyday awareness. Now, get comfortable. Let your body settle into whatever surface supports you. Allow your breathing to slow and deepen, and imagine the solid ground beneath you not as an impermeable barrier, but as a living, breathing system where water moves with gentle persistence through countless hidden channels and pathways. Tonight, we're going to discover how every footstep you take rests above a world of flowing water, how every building, every street, every garden exists above networks of underground rivers that have been flowing since long before human civilization began, and continue flowing with quiet determination toward destinations that connect the hidden world beneath our feet to the visible world around us. Take a slow breath. Feel yourself supported by this foundation of flowing water, and let's begin. In this very moment, as you rest comfortably in your chosen spot, countless drops of water are moving through the soil and rock layers beneath you, following pathways that began their journey perhaps yesterday with a gentle rainfall, or perhaps decades ago from mountain snowmelt hundreds of miles away, or even centuries ago from ancient precipitation that has been traveling slowly through deep underground systems with the patient persistence that water brings to all its movements through the hidden landscapes that exist below the surface of our awareness. The ground beneath your feet, which appears solid and permanent from your surface perspective, is actually a complex, three-dimensional network of spaces and passages where water flows in streams without visible banks, rivers without defined channels, and vast underground lakes that exist in the spaces between rock particles, in fractures that opened millions of years ago, and in caverns carved by the gentle but persistent action of moving water over time frames that dwarf human experience, but represent mere moments in the Earth's patient history of water circulation. Every square foot of land surface above you connects to this hidden aquatic world through millions of tiny pathways that begin at the very surface where raindrops first contact soil, leaves, and rock surfaces. These initial contact points represent the beginning of journeys that might last hours, days, years, or even centuries, as water finds its way through increasingly complex networks of underground passages that guide its movement according to principles of gravity, geology, and the fundamental physics that govern how liquids move through porous materials. The soil layer directly beneath the surface serves as the first gateway into this underground world, acting as both filter and distribution system that determines how surface water will begin its hidden journey into the depths below. This soil layer, which might appear to be simple dirt from a surface perspective, actually consists of countless particles of different sizes, shapes, and compositions that create a complex network of spaces and passages where water can move, pause, change direction, and interact with minerals, organic matter, and living organisms that make their homes in this interface between the surface and underground worlds. Within the top few inches of soil, water movement follows patterns that blend the orderly with the chaotic, as gravity pulls water generally downward, while the irregular shapes and sizes of soil particles create countless opportunities for water to move horizontally, to pull temporarily in small spaces, to interact with plant roots and soil organisms, and to begin the chemical transformations that will continue throughout its underground journey. This surface soil zone represents a busy intersection where atmospheric water first encounters the solid earth and begins the slow transformation from freely falling precipitation to underground flow. The spaces between soil particles, called pore spaces, create the pathways through which water begins its underground journey, and these spaces vary dramatically in size, shape, and connectivity depending on the composition and structure of the local soil. Clay soils create networks of very small pore spaces that slow water movement and encourage horizontal flow, while sandy soils provide larger pore spaces that allow water to move more quickly toward deeper underground systems. The size and arrangement of these pore spaces determine not just how fast water moves, but also how much water can be stored temporarily in the soil system, and how much will continue its journey toward deeper underground layers. As water moves through soil, it begins to acquire the chemical signature that will characterize its underground journey, dissolving tiny amounts of minerals from soil particles, picking up organic compounds from decaying plant matter, and undergoing chemical changes that reflect the specific geological and biological conditions of its local environment. This chemical evolution continues throughout the water's underground journey, creating a kind of molecular memory that preserves information about every layer, every rock type, and every biological system that the water encounters during its slow movement through the hidden landscapes beneath our feet. The transition from soil to deeper underground systems occurs gradually, without clear boundaries, as soil gives way to weathered rock, which in turn gives way to solid bedrock that contains its own network of fractures, fissures, and porous zones where water can continue its hidden journey. This transition zone, called the vadose zone or unsaturated zone, represents a region where water movement becomes increasingly influenced by the structure and composition of the underlying geology, while still remaining connected to surface processes through the soil system above. Plant roots create their own network of channels and modifications to the underground water system, extending down into soil and rock layers to access underground water sources while simultaneously creating pathways that can guide water movement in new directions. These biological modifications to the underground landscape demonstrate how living systems and water systems interact to create environments that serve the needs of both, with plant roots following underground water sources while also modifying the underground environment in ways that affect future water movement patterns. The temperature of underground water begins to change as it moves away from surface influences and enters the more stable thermal environment of the underground world. Surface water temperatures fluctuate dramatically with daily and seasonal changes, but underground water temperatures become increasingly stable with depth, approaching the average annual air temperature of the region at depths of just a few feet, and continuing to warm gradually with greater depth due to geothermal heat from the Earth's interior. This thermal stability of underground water creates environments that remain hospitable to life even when surface conditions become extremely hot or cold. The first underground streams begin to form as water moving through soil and weathered rock encounters less permeable layers that encourage horizontal flow, creating the beginnings of organized flow patterns that will develop into the hidden river systems that characterize deeper underground environments. These incipient streams might flow for only a few feet or a few yards before dispersing again into the general underground water system, but they represent the emergence of organized flow patterns that will become more pronounced and persistent as water continues its journey into deeper underground systems. Seasonal patterns in surface precipitation create rhythmic variations in the underground water system, with periods of heavy rainfall or snowmelt creating pulses of increased underground flow that can be detected in deeper underground systems weeks or months after the surface precipitation occurred. These seasonal signals propagate through the underground water system like slow-motion waves, carrying information about surface conditions into the hidden depths and creating temporal connections between surface weather patterns and underground water availability that demonstrate the intimate connections between visible and hidden water systems. The chemistry of underground water continues to evolve as it encounters different types of rock and soil materials, with some minerals dissolving easily in moving water while others remain essentially unchanged by contact with underground flow. Limestone and other carbonate rocks contribute calcium and bicarbonate ions to underground water, creating the slightly alkaline conditions that characterize many underground water systems, while granite and other igneous rocks contribute different mineral signatures that reflect their unique geological origins and chemical compositions. Underground water movement creates its own microenvironments that support specialized communities of microorganisms adapted to life in the hidden aquatic world beneath our feet. These underground biological communities process nutrients, break down organic matter, and contribute to the chemical evolution of underground water while creating biological systems that exist entirely outside the influence of surface sunlight and weather patterns. The presence of these underground biological communities demonstrates that the hidden water world beneath our feet is not a sterile, purely physical system, but rather a living environment that supports its own unique forms of life. The pressure environment of underground water systems increases gradually with depth as the weight of overlying soil, rock, and water creates higher pressures that affect how water moves through underground spaces and how it interacts with the surrounding geological materials. These pressure changes influence the solubility of different minerals, the behavior of dissolved gases, and the physical properties of the water itself, creating depth-dependent changes in underground water systems that reflect the changing physical conditions encountered as water moves deeper into the Earth's interior. Groundwater flow patterns begin to emerge as water moving through underground systems encounters geological structures that guide and direct flow in preferred directions. Fractures in bedrock, contact zones between different rock types, and buried river valleys filled with permeable sediments all create pathways that concentrate underground flow and begin to create the organized flow systems that will develop into major underground river networks in deeper parts of the underground water system. The connection between surface water and underground water becomes apparent as streams, lakes, and wetlands either contribute water to underground systems or receive water from underground sources, depending on the local geological conditions and the relative water levels in surface and underground systems. These connections create dynamic relationships between visible and hidden water systems that change seasonally and over longer time periods as underground water levels fluctuate in response to precipitation patterns, climate variations, and human activities that affect water movement and storage throughout the integrated surface and underground water system. Timescales in the underground water system operate according to principles that are fundamentally different from surface water movement, with underground water often moving so slowly that individual molecules might remain in underground systems for decades, centuries, or even millennia before returning to surface environments. This slow movement creates opportunities for extensive chemical and biological interactions between water and the surrounding underground environment, while also creating water storage systems that preserve precipitation from past climatic periods and make it available for current and future needs. The quiet persistence of underground water movement creates a hidden soundtrack of flowing water that continues constantly beneath our feet, even in regions where surface water is scarce or absent entirely. This hidden flowing creates subtle sounds that can sometimes be detected in caves, wells, and other openings that provide access to underground water systems, revealing the constant movement and activity that characterizes the underground water world even when it remains invisible from surface perspectives. Imagine a single raindrop that has just completed its fall from a cloud above, landing softly on the soil surface near where you rest, beginning a journey that will transform it from freely moving atmospheric moisture into part of the vast underground water system that flows beneath your feet. This journey downward through soil and rock represents one of nature's most patient and persistent processes, unfolding with a deliberate slowness that allows for countless interactions, transformations, and connections as water gradually transitioned from the surface world into the hidden realm of underground flow. The initial moments of this downward journey involve the raindrop's interaction with the soil surface, where it encounters a complex landscape of soil particles, organic matter, plant material, and tiny air spaces that will determine how quickly and in which direction the water will begin its underground movement. The soil surface acts like a sophisticated sorting and distribution system, with some water immediately beginning to infiltrate into pore spaces between soil particles, while other water might flow horizontally across the surface until it finds more permeable areas where downward movement can begin. Soil composition plays a crucial role in determining the character of this initial downward movement, with clay-rich soils creating networks of very small pore spaces that slow water movement and encourage thorough interaction between water and soil particles, while sandy soils provide larger pathways that allow more rapid downward movement, but less opportunity for chemical and biological interactions. The specific mixture of particle sizes in any given soil creates a unique hydraulic environment that gives each underground water system its own characteristic pattern of water movement and chemical evolution. The process of infiltration occurs grain by grain and pore space by pore space, as water molecules find pathways through the complex three-dimensional maze created by soil particle arrangements. This infiltration happens through a combination of gravity, which pulls water generally downward, and capillary action, which allows water to move in any direction through very small spaces due to the molecular attraction between water molecules and solid surfaces. The balance between these forces creates movement patterns that are both predictable in their general direction and chaotic in their specific pathways. As water moves through the upper soil layers, it begins to encounter the roots of plants, which have created their own network of channels and modified spaces within the soil structure. Plant roots actively extract water from soil pore spaces for their biological needs, but they also create preferential pathways for water movement through root channels that remain after roots decay and through the loosened soil that surrounds active root systems. This biological modification of soil structure demonstrates how living systems and water systems co-evolve to create mutually beneficial arrangements. The chemical evolution of infiltrating water begins immediately upon contact with soil particles, as water dissolves tiny amounts of minerals from soil grains and picks up organic compound from decomposing plant and animal matter. This chemical evolution is particularly active in the upper soil layers, where biological activity is highest and where the greatest variety of chemical compounds are available for dissolution. The water gradually acquires a chemical signature that reflects the specific geological and biological characteristics of its local environment. Temperature changes accompany the downward journey as water moves from the variable thermal environment at the surface into the more stable temperature regime of the underground system. Surface temperatures can fluctuate dramatically over daily and seasonal cycles, but soil temperatures become increasingly stable with depth, approaching the mean annual air temperature at depths of just a few feet. This thermal transition affects the rate of chemical reactions, the solubility of different minerals, and the activity of biological organisms that inhabit the soil environment. The unsaturated zone, also called the vadose zone, represents the region above the water table where soil and rock pore spaces contain both air and water, creating a complex environment where water movement is influenced by both gravity and capillary forces. In this zone, water moves primarily downward under the influence of gravity, but it can also move horizontally or even upward through capillary action, especially in fine-grained materials where molecular forces can overcome gravitational forces over short distances. Percolation through this unsaturated zone occurs at rates that vary dramatically depending on soil and rock properties, with water movement ranging from inches per day in permeable sandy materials to inches per year in tight clay formations. This variation in percolation rates creates diverse underground environments where some water moves relatively quickly toward deeper underground systems, while other water remains in the upper soil layers for extended periods, providing long-term water storage that supports plant growth and biological activity during dry periods. The moisture content of soil in the unsaturated zone creates a dynamic balance between water moving downward toward the water table and water being extracted upward by plant roots or lost to evaporation at the surface. This balance changes constantly in response to precipitation events, seasonal cycles, and longer-term climate variations, creating a dynamic interface between surface and underground water systems that respond sensitively to environmental changes while maintaining overall system stability. Layered soil and rock structures create complex patterns of water movement as percolating water encounters materials with different permeabilities and hydraulic properties. When downward moving water encounters a less permeable layer, it may spread horizontally above that layer, creating temporary perched water tables that support local wetland conditions or seasonal springs. These perched systems demonstrate how the underground water system can create surface water features that exist only temporarily or seasonally, depending on underground conditions. The development of preferential flow paths occurs as water repeatedly follows the same routes through soil and rock systems, gradually enlarging and improving these pathways through the physical and chemical processes associated with flowing water. Over time, these preferential paths become more prominent and efficient, creating organized drainage networks within the underground system that concentrate water flow and create the beginnings of underground stream systems. Seasonal variations in infiltration and percolation create rhythmic patterns in underground water movement, with spring snowmelt and summer rainfall events creating pulses of increased water movement that propagate downward through the unsaturated zone at rates determined by local soil and rock properties. These seasonal signals can be tracked as they move through underground systems, creating temporal connections between surface precipitation events and changes in underground water levels that occur weeks or months later. The role of organic matter in soil creates special chemical environments that affect water movement and chemical evolution as water percolates through biologically active soil layers. Organic acids produced by decomposing plant material can accelerate the dissolution of certain minerals, while organic compounds can form complexes with dissolved metals that affect their mobility and chemical behavior. These biological influences on water chemistry demonstrate how living systems contribute to the character and quality of underground water. Fracture flow in bedrock represents a different mode of water movement that becomes increasingly important as percolating water reaches consolidated rock layers beneath the soil system. Fractures in bedrock, created by geological processes including tectonic stress, thermal expansion and contraction, and chemical weathering, provide pathways for water movement that can be much faster than movement through porous media. These fracture systems often create complex, three-dimensional networks that can transport water rapidly across considerable distances. The transition from diffuse pore space flow to organized fracture flow marks a significant change in the character of underground water movement, as water begins to concentrate in discrete pathways rather than moving through distributed pore networks. This transition often occurs gradually over depths ranging from a few feet to hundreds of feet, depending on local geological conditions and the depth to competent bedrock that contains well-developed fracture systems. Groundwater mounding occurs when infiltrating water encounters low permeability layers or high water table conditions that cause water to accumulate temporarily in subsurface zones, creating elevated water levels that can influence surface water conditions and create seasonal wetlands or springs. These mounded conditions demonstrate how underground water storage can affect surface hydrology and create dynamic relationships between underground and surface water systems. The chemical stratification of infiltrating water develops as water moving through different soil and rock layers acquires different chemical signatures that reflect the materials it has contacted during its downward journey. Water that has moved through limestone layers will have different chemical characteristics than water that has percolated through granite or sandstone, creating chemical fingerprints that preserve information about the underground pathways followed by different portions of the infiltrating water. Residence time in the unsaturated zone varies dramatically, with some water moving from surface to water table in days or weeks, while other water may remain in the unsaturated zone for years or decades, depending on the depth to groundwater, the permeability of intervening materials, and the local climate conditions that affect recharge and evapotranspiration rates. This variation in residence times creates diverse chemical and biological environments within the unsaturated zone. The formation of soil horizons creates layered environments with different hydraulic properties that affect water movement patterns and create opportunities for horizontal flow, temporary water storage, and complex chemical interactions. These horizon-controlled flow patterns can create seasonal water tables, support unique plant communities, and contribute to the development of surface water features that reflect underground water conditions. Evapotranspiration processes create upward water movement that competes with downward percolation, as plant roots extract water from soil-poor spaces and transport it to leaves where it evaporates into the atmosphere. This upward water movement can significantly reduce the amount of water that reaches deeper underground systems, particularly in arid and semi-arid environments where evapotranspiration rates are high relative to precipitation rates. The capillary fringe represents the zone immediately above the water table, where capillary forces hold water in soil-poor spaces despite the presence of the free water surface below. This zone creates a transition between the unsaturated zone above and the saturated zone below, and it can rise and fall in response to changes in water table elevation. The capillary fringe provides water storage that can support plant growth during dry periods and contributes to the complex interactions between surface and underground water systems. Preferential infiltration areas develop where surface conditions create particularly favorable opportunities for water to enter underground systems, including areas with coarse-grained soils, fractured bedrock exposure, or biological activity that has created enhanced soil permeability. These areas often become focused recharge zones that contribute disproportionately to underground water systems despite representing relatively small portions of the total land surface. The development of macropores in soil, created by earthworm activity, root decay, freeze-thaw cycles, and other biological and physical processes, provides pathways for rapid water infiltration that can bypass the slower matrix flow through soil-poor spaces. These macropore systems can transport water rapidly from surface to deeper underground systems, creating opportunities for contaminants or nutrients to reach groundwater more quickly than would be expected based on average soil permeability. Interaction with soil organisms creates biological influences on water movement and chemistry, as infiltrating water encounters bacteria, fungi, invertebrates, and plant roots that modify water chemistry, create or block flow pathways, and contribute organic compounds that affect water quality. These biological interactions demonstrate that the journey of water through soil and rock is not purely a physical and chemical process, but also involves complex interactions with living systems that influence water movement and transformation. The gradual transition from infiltration to groundwater flow occurs as percolating water approaches the water table and begins to encounter increasingly saturated conditions, where water movement becomes dominated by hydraulic gradients rather than gravitational forces alone. This transition marks the beginning of true groundwater flow, where water becomes part of regional flow systems that can transport water over considerable distances through underground pathways that connect recharge areas to discharge locations that may be miles or even hundreds of miles away. The journey downward through soil and rock represents a fundamental transformation of water from freely moving atmospheric moisture to underground water that becomes part of regional flow systems with their own hydraulic characteristics, chemical signatures, and temporal patterns. This transformation occurs gradually and peacefully, with each step in the downward journey contributing to the development of underground water systems that provide essential connections between surface precipitation and underground storage, between recharge areas and discharge zones, and between different time periods as water moves slowly through systems that preserve and transport water across timescales ranging from seasons to centuries. Deep beneath the surface where you rest, in the hidden landscape that exists below the reach of sunlight and weather, water flows in rivers that have no visible banks, no defined channels carved by erosion, no rippling surfaces that catch light and reveal their presence to casual observation. These underground rivers exist in the spaces between rock particles, in networks of fractures that thread through solid bedrock, and in vast porous formations where water moves with the same persistence as surface streams, but following principles of flow that create entirely different landscapes and entirely different relationships between water and the solid earth that surrounds and guides its movement. The concept of underground rivers challenges our surface-based understanding of how water can flow, as these hidden waterways operate according to principles that blend the behavior of rivers with the behavior of water moving through sponges, creating flow systems that are simultaneously organized and distributed, fast and slow, concentrated and dispersed. depending on the geological materials through which they move and the hydraulic forces that drive their persistent journey toward distant destinations that may be located hundreds or thousands of feet below ground or hundreds of miles away from their points of origin. Porous media flow represents the most common form of underground river movement, where water moves through networks of connected pore spaces and sediments and rocks that have been deposited, compacted, and modified by geological processes over millions of years. These porous materials create three-dimensional networks of pathways where water can move in response to hydraulic gradients, following routes that are determined by the size, shape, and connectivity of pore spaces rather than by the gravitational forces that dominate surface stream flow. The hydraulic conductivity of different geological materials determines how easily water can move through underground systems, with highly permeable materials like coarse sand and gravel allowing rapid water movement, while fine-grained materials like clay and shale restrict water movement to very slow rates that may measure inches per year rather than feet per day. This variation in hydraulic conductivity creates a landscape of underground flow velocities that ranges across many orders of magnitude, from underground rivers that flow faster than surface streams to underground systems where water moves so slowly that individual molecules may remain in the system for thousands of years. Darcy's law governs the movement of water through porous underground systems, describing how flow rate depends on the permeability of the geological materials, the hydraulic gradient that drives flow, and the properties of the water itself. This fundamental relationship creates underground flow patterns that respond to changes in water levels, seasonal recharge variations, and regional geological structures in ways that create organized flow systems despite the apparently random distribution of pore spaces in underground materials. Groundwater flow systems develop characteristic patterns that reflect the three-dimensional distribution of permeable and impermeable materials in the underground environment, creating flow paths that can extend from local systems with flow lengths measured in hundreds of feet to regional systems that transport water across entire geographic basins over distances measured in hundreds of miles. These flow systems operate simultaneously at multiple scales, with local systems nested within intermediate systems, which are in turn nested within regional systems that create hierarchical flow networks of extraordinary complexity and extent. The water table represents the upper surface of the saturated zone, where underground rivers begin to flow as continuous systems rather than as the discontinuous, gravity-driven flow that characterizes the unsaturated zone above. Below the water table, all available pore spaces and fractures are filled with water, creating conditions where water movement is driven by hydraulic gradients rather than by gravity alone, and where flow can occur in any direction depending on the distribution of hydraulic head throughout the underground system. Equipotential lines and flow nets provide mathematical tools for understanding and visualizing the patterns of underground river flow, showing how water moves from areas of high hydraulic head to areas of low hydraulic head along pathways that are perpendicular to lines of equal hydraulic potential. These flow patterns create elegant geometric relationships that reveal the underlying order within apparently chaotic underground systems, demonstrating how mathematical principles govern the movement of underground rivers just as they govern all other natural flow systems. Confined and unconfined aquifer systems create different types of underground river environments, with unconfined aquifers allowing direct interaction between underground flow and surface recharge, while confined aquifers create pressurized underground flow systems that can transport water over great distances without direct connection to surface water sources. Confined aquifers often create artesian conditions where underground water pressure is sufficient to drive water upward through wells or natural openings, creating surface springs that reveal the presence and pressure of underground river systems. Heterogeneity in underground materials creates complex flow patterns as underground rivers encounter geological formations with dramatically different hydraulic properties, causing flow to speed up in permeable zones, slow down in tight formations, and change direction in response to structural features like faults, fractures, and contact zones between different rock types. This geological heterogeneity creates underground landscapes that are far more complex and varied than surface topography, with underground mountains and valleys, ridges and depressions that exist only in the hydraulic realm and affect flow patterns in ways that are invisible from surface perspectives. Fracture flow systems represent a different class of underground rivers, where water moves through networks of fractures in consolidated rock rather than through pore spaces in unconsolidated sediments. These fracture systems can create underground rivers that flow much faster than porous media systems, with flow velocities that can approach or even exceed those of surface streams. Fracture networks often create highly anisotropic flow systems, where water moves much more easily in certain directions than in others, depending on the orientation and connectivity of fracture systems. Karst aquifer systems develop in soluble rocks like limestone and gypsum, where underground rivers have chemically dissolved pathways that can grow to become true underground streams with defined channels, underground pools, and even underground waterfalls. These karst systems represent the closest underground analogs to surface river systems, with organized drainage networks that can transport large volumes of water through well-defined underground channels that may extend for many miles through the dissolved rock. Spring systems reveal the emergence of underground rivers back to the surface world, creating locations where the hidden flow systems that exist beneath our feet become visible and accessible to surface observation. Springs represent the discharge points of underground flow systems, where hydraulic gradients drive underground water to the surface through natural openings in the geological framework. The characteristics of springs, their flow rates, temperatures, and chemical compositions, provide windows into the underground river systems that feed them. Base flow in surface streams represents the continuous contribution of underground rivers to surface water systems, demonstrating the intimate connections between hidden underground flow and visible surface flow. During dry periods when surface runoff is minimal, underground discharge maintains flow in surface streams, rivers, and wetlands, revealing how underground rivers provide essential support for surface water ecosystems and human water supplies, even when their presence remains largely invisible. Underground watersheds and groundwater divides create hidden boundaries that separate different underground river systems and determine which underground flow systems will discharge to which surface water bodies. These underground drainage boundaries may be completely different from surface watershed boundaries, creating situations where precipitation that falls in one surface watershed may actually contribute to underground flow systems that discharge in completely different surface watersheds, demonstrating the complex, three-dimensional nature of underground flow systems. Hydraulic gradients drive underground river flow by creating pressure differences that cause water to move from areas of high hydraulic head to areas of low hydraulic head, following pathways through underground systems that minimize energy loss while transporting water toward discharge locations. These hydraulic gradients are created by elevation differences, recharge and discharge patterns, and geological structures that create barriers or preferential pathways for underground flow. Storage and transmission properties of underground river systems allow these hidden aquatic environments to store vast quantities of water while simultaneously transmitting flow from recharge areas to discharge zones over timescales that can range from days to millennia. The storage capacity of underground systems often far exceeds that of surface water systems, creating underground reservoirs that can sustain flow during extended dry periods and buffer the effects of climate variability on water availability. Dispersion and mixing processes in underground rivers create chemical environments where waters from different sources and different time periods blend gradually as they move through underground systems, creating chemical signatures that reflect the integration of multiple water sources over extended time periods. This mixing creates underground water with chemical characteristics that may be very different from any of the individual source waters that contribute to the underground system. Velocity variations within underground river systems create flow environments where some portions of the water move much faster than others, depending on the local permeability characteristics and the detailed geometry of flow pathways. This velocity variation creates opportunities for some water to reach discharge points relatively quickly, while other water from the same source area may remain in the underground system for much longer periods, creating age distributions in underground water that can span many decades or centuries. Seasonal and long-term variations in underground river flow reflect the response of these systems to changing recharge conditions, with increased flow during wet periods and decreased flow during dry periods, but with response times that are typically much slower than surface water systems due to the dampening effects of underground storage and the slower transmission characteristics of underground flow pathways. Temperature characteristics of underground rivers reflect their isolation from surface temperature variations, with underground water temperatures remaining relatively stable throughout seasonal cycles and approaching the mean annual air temperature of the recharge area. This thermal stability creates underground environments that provide refugia for temperature-sensitive organisms and create unique ecological conditions that are largely independent of surface climate variations. Chemical evolution of underground rivers occurs as flowing water interacts with the geological materials through which it moves, dissolving some minerals while precipitating others, and gradually acquiring chemical signatures that reflect the specific geological formations encountered during underground flow. This chemical evolution can continue for centuries or millennia as water moves through lengthy underground flow paths, creating opportunities for extensive water-rock interactions that profoundly modify water chemistry. Underground river networks often display fractal characteristics where smaller tributary systems feed into larger underground streams, which in turn contribute to major underground flow systems, creating hierarchical drainage networks that parallel the organization of surface river systems but operate according to the different physical principles that govern flow through porous and fractured underground systems. Interaction zones between different underground river systems create mixing environments where waters with different chemical signatures, temperatures, and ages blend to create hybrid waters that represent the integration of multiple underground flow systems. These interaction zones often occur at geological boundaries where different aquifer systems come into contact, creating opportunities for complex chemical and biological processes that affect water quality and ecological conditions. The persistence of underground river flow creates hidden aquatic environments that provide continuous water movement and circulation even in regions where surface water is scarce or entirely absent, demonstrating how underground systems can maintain hydrological connectivity across landscapes that appear to be water-limited from surface perspectives. This persistence creates opportunities for ecological communities and biogeochemical processes that depend on continuous water availability, while also providing reliable water sources that can sustain human activities in water-scarce environments. Underground rivers represent one of Earth's most extensive and important water systems, transporting more water over longer distances and for longer periods than any surface water system, while remaining largely invisible and unrecognized by surface-dwelling observers. These hidden rivers create the foundation for much of the world's water supply, ecological function, and climate regulation, operating with quiet persistence beneath our feet and supporting the visible world above through their continuous, patient circulation through the underground landscapes that exist in the spaces between the solid particles that make up the Earth's crust. Stretching out in all directions beneath the solid ground where you rest lies a vast and complex landscape that exists entirely below the surface of ordinary perception, a three-dimensional world of underground formations and hidden topography that rivals the complexity of any surface mountain range or river valley system. This underground landscape possesses its own mountains and valleys, its own ridges and depressions, its own barriers and highways that guide water movement through pathways that follow the underground topography of rock layers, geological structures, and aquifer systems that have been shaped by millions of years of geological processes operating far beneath the reach of surface weathering and erosion. The water table creates the fundamental topographic surface of this underground landscape, forming an invisible boundary that separates the unsaturated zone above from the saturated zone below, and creating underground hills and valleys that roughly mirror surface topography, but with much gentler gradients and smoother transitions between high and low areas. This underground topographic surface rises beneath hills and ridges where groundwater recharge is enhanced, and drops beneath valleys and lowlands where groundwater discharge creates springs, wetlands, and base flow contributions to surface streams. Aquifer systems form the major geological formations of this underground landscape, creating distinct underground regions with characteristic water-bearing properties, flow velocities, and chemical environments that can extend for hundreds or thousands of square miles beneath the surface. These aquifer systems represent underground provinces that may bear little resemblance to surface geographical divisions, creating hidden boundaries and territories that exist independently of surface watersheds, political boundaries, or ecological regions visible from above ground. Perched aquifer systems create underground plateaus and mesas where local impermeable layers trap infiltrating water above the regional water table, forming isolated underground water bodies that exist like underground lakes suspended above the main groundwater system. These perched systems often support unique ecological communities and can create seasonal springs and wetlands that appear and disappear based on local recharge conditions, demonstrating how underground topography can create surface features that seem to exist independently of regional water patterns. Confined aquifer systems form underground pressure vessels where water-bearing formations are sandwiched between impermeable layers that prevent vertical water movement and create pressurized underground environments where water can flow great distances while maintaining hydraulic head that exceeds the elevation of the land surface above. These confined systems create underground rivers under pressure that can transport water across entire continents, while remaining completely isolated from surface water systems. Hydraulic gradients create the underground equivalent of slopes and valleys, forming invisible inclines where water flows from areas of high hydraulic head toward areas of lower hydraulic head, following underground topography that is determined by water pressure and elevation rather than by simple gravitational slopes. These hydraulic gradients can create underground water movement that flows uphill from a surface perspective, demonstrating how underground topography operates according to different principles than surface topography. Groundwater divides form underground ridges and watersheds that separate different groundwater flow systems and determine which underground rivers will flow toward which discharge areas, creating hidden boundaries that may be completely different from surface watershed divides. These underground divides can shift position in response to changes in recharge patterns, pumping activities, or seasonal variations in groundwater levels, creating dynamic underground boundaries that change over time in ways that surface topographic divides do not. Aquifer boundaries create underground cliffs and contact zones where geological formations with dramatically different hydraulic properties meet, causing abrupt changes in flow velocity, water chemistry, and ecological conditions that can be as dramatic as the transition from land to water at a surface shoreline. These aquifer boundaries often become zones of enhanced chemical activity where different water types mix and react, creating unique underground environments with distinctive chemical and biological characteristics. Fracture networks create underground canyon systems and valley networks where water can flow rapidly through interconnected networks of rock fractures that may extend for many miles through consolidated bedrock. These fracture systems often follow structural patterns related to tectonic stress, creating underground drainage networks with preferred orientations that may be completely unrelated to surface topographic patterns, but which create highly organized underground flow systems. Karst landscapes represent the most dramatic expressions of underground topography, where chemical dissolution of soluble rocks has created true underground caverns, rivers, and lakes that approach surface landscapes in their organization and complexity. These karst systems can include underground waterfalls, underground pools, and underground drainage networks that rival surface river systems in their organization and flow capacity, creating underground landscapes that are remarkably similar to surface topography. Paleochannels form buried underground valleys where ancient surface rivers were covered by later geological deposits, creating underground highways for groundwater flow that follow the paths of rivers that may have flowed millions of years ago. These buried river valleys often represent the most permeable pathways in underground systems, concentrating groundwater flow along routes that preserve the drainage patterns of ancient surface landscapes that no longer exist above ground. Saltwater interfaces create underground boundaries between fresh and saline groundwater that can extend for hundreds of miles inland from ocean coastlines, forming invisible underground shorelines where fresh water flowing toward the ocean encounters denser salt water moving inland from marine sources. These interfaces create dynamic underground boundaries that fluctuate with tidal cycles, seasonal variations in freshwater flow, and longer-term changes in sea level and climate patterns. Underground storage systems create vast underground reservoirs where aquifer formations can store quantities of water that dwarf the storage capacity of surface lakes and reservoirs, holding water in underground spaces that may have total volumes comparable to entire surface watersheds. These underground storage systems often represent the primary water reserves for entire regions, storing water that accumulated over decades, centuries, or millennia, and releasing it slowly to support surface ecosystems and human water supplies. Recharge zones form the underground equivalent of mountain watersheds, representing surface areas where precipitation and surface water can efficiently infiltrate into underground systems and begin their journey through underground flow networks toward distant discharge areas. These recharge zones often coincide with areas of permeable surface materials, fractured bedrock, or favorable topographic conditions that enhance infiltration and groundwater replenishment. Discharge zones create underground valleys and lowlands where groundwater flow converges and emerges back to the surface world through springs, seeps, wetlands, and base flow contributions to surface streams. These discharge zones represent the downstream ends of underground flow systems, where water that may have traveled for decades or centuries through underground pathways finally returns to surface environments, often with chemical signatures that preserve information about the underground landscapes through which the water has traveled. Underground flow convergence zones create underground confluences where multiple groundwater flow systems come together, mixing waters with different chemical signatures, ages, and flow histories to create hybrid underground waters that represent the integration of multiple underground watersheds. These convergence zones often become areas of enhanced biological activity where the mixing of different water types creates favorable conditions for underground ecosystems. Barrier systems in underground landscapes form underground dams and flow restrictions, where low permeability geological formations restrict groundwater movement and create underground ponding that can extend for miles behind geological barriers. These underground barriers can create dramatic differences in water levels and flow conditions across relatively short distances, demonstrating how underground topography can create abrupt transitions between different hydraulic environments. Underground thermal landscapes develop where geothermal heat sources create temperature variations in groundwater systems, forming underground thermal provinces where water temperatures may be elevated significantly above normal groundwater temperatures. These thermal zones create unique underground environments that support specialized biological communities and can create surface thermal features like hot springs and geysers that reveal the presence of underground thermal landscapes. Vertical zonation in underground systems creates underground layering where different depths have distinctly different hydraulic, chemical, and biological characteristics, forming underground stratigraphic sequences that may extend from shallow, rapidly circulating groundwater to deep, ancient groundwater that has been isolated from surface influences for thousands or millions of years. This vertical zonation creates underground environments that change dramatically with depth, much like ecological zonation in surface environments changes with elevation. Underground pressure landscapes develop where confined aquifer systems create variations in hydraulic head that can differ dramatically from surface elevations, forming invisible underground topography where pressure rather than elevation determines the direction and rate of water movement. These pressure landscapes can create underground flow patterns that appear to defy gravity from a surface perspective, with water flowing from low surface elevations toward high surface elevations in response to underground pressure gradients. Seasonal variations in underground landscapes create dynamic changes in water table elevations, flow directions, and hydraulic gradients that cause the underground topography to shift and change in response to varying recharge and discharge conditions. During wet seasons, underground water levels rise and flow systems expand, while during dry seasons, water levels drop and some flow systems may become disconnected or cease flowing entirely, creating seasonal changes in underground landscape connectivity. Anisotropy in underground flow systems creates underground landscapes where flow characteristics vary dramatically with direction, much like surface landscapes, where travel may be much easier in some directions than in others. This anisotropy can be caused by layered geological formations, fracture orientations, or structural features that create preferred directions for groundwater flow, resulting in underground drainage patterns that may be very different in different directions. Underground ecological zonation creates distinct biological provinces within groundwater systems where different combinations of chemistry, temperature, flow velocity, and residence time support different communities of groundwater organisms. These underground ecological zones can be as distinct and specialized as surface ecological communities, with endemic species adapted to specific underground environmental conditions that may exist nowhere else on Earth. Scale dependencies in underground landscapes create situations where underground topographic features that are significant at local scales may be completely overwhelmed by regional scale features, much like surface landscapes where local hills and valleys exist within larger mountain ranges or plains. Understanding underground landscapes requires appreciation of how features at different scales interact to create the overall underground topographic complexity that guides groundwater flow and creates underground environmental diversity. The dynamic nature of underground landscapes reflects their response to changing boundary conditions, including climate variations, land use changes, and human activities that affect recharge and discharge patterns. Unlike surface landscapes that change primarily through erosion and deposition over geological timescales, underground landscapes can change relatively rapidly in response to changes in hydraulic conditions, demonstrating how underground systems can be both stable over long periods and dynamic in response to changing conditions. Recognition of underground landscape complexity has revolutionized understanding of groundwater systems and their role in supporting surface ecosystems, human water supplies, and global water circulation. This hidden topographic world beneath our feet operates according to principles that create landscape features and flow systems as complex and varied as any surface landscape, while remaining largely invisible and unrecognized by surface-based observation and conventional topographic mapping techniques that reveal only the visible portion of Earth's total landscape complexity. In the deepest reaches of the underground systems that extend far beneath where you rest, there flows water so ancient that it fell as rain when the Earth's continents occupied completely different positions, when ice sheets covered regions that are now temperate, when the ancestors of modern plants and animals were just beginning their evolutionary journeys toward the forms we recognize today. This ancient water moves through underground pathways with such patient slowness that individual molecules may have been traveling through subterranean systems for thousands, tens of thousands, or even hundreds of thousands of years, carrying with them chemical memories of past climates, past atmospheric compositions, and past environmental conditions that existed long before human civilization appeared on Earth. The age of groundwater creates temporal landscapes beneath our feet where different zones contain water from different periods in Earth's history, forming underground archaeological layers where the deepest, most ancient waters preserve information about environmental conditions that existed during past ice ages, ancient warm periods, and transitional climate phases that occurred over timescales that dwarf recorded human history. These temporal zones create opportunities for scientists to study past climate conditions by analyzing the chemical composition of ancient groundwater that has been preserved in deep underground systems. Radioactive decay dating of groundwater uses naturally occurring isotopes like carbon, 14, tritium, and chlorine, 36 to determine when groundwater was last in contact with the atmosphere, providing techniques for measuring the age of underground water with precision that can distinguish between water that infiltrated decades ago and water that has been underground for tens of thousands of years. These dating techniques reveal that groundwater age increases generally with depth and distance from recharge areas, but with complex patterns that reflect the detailed geometry of underground flow systems. Paleoclimatic signatures preserved in ancient groundwater include chemical indicators of past temperature, precipitation, and atmospheric composition that allow reconstruction of environmental conditions that existed when the water first entered underground systems. These signatures may include isotope ratios that reflect past temperature patterns, dissolved atmospheric gases that preserve information about past atmospheric composition, and mineral dissolution patterns that indicate the chemical environment that existed during past recharge periods. Ice Age recharge represents some of the most ancient water found in contemporary groundwater systems, having infiltrated during periods when continental ice sheets covered large portions of North America and Europe, creating recharge conditions that were dramatically different from contemporary patterns. This Ice Age water often has chemical signatures that reflect the presence of permafrost, the enhanced dissolution of atmospheric carbon dioxide in cold water, and the interaction with glacial materials that no longer exist in the recharge areas where this ancient water originated. Deep circulation systems transport ancient water through underground pathways that may extend hundreds of miles from recharge areas to discharge zones, creating flow systems where water travels so slowly that residence times in underground systems can exceed the duration of entire Ice Age cycles. These deep circulation systems often transport water from highland recharge areas to lowland discharge areas through underground pathways that follow regional geological structures and cross multiple surface watersheds during their lengthy underground journeys. Connate water represents the most ancient groundwater, consisting of water that was trapped in sedimentary rocks during their original deposition millions or even billions of years ago, preserving chemical signatures of ancient oceans and atmospheric conditions that existed during completely different geological periods. This connate water has often been modified by high temperatures and pressures during its long residence in deep underground systems, but it can still preserve information about environmental conditions that existed during the early history of Earth's water cycle. Fossil aquifer systems contain ancient water that accumulated during past periods of enhanced recharge, but which are now isolated from contemporary recharge processes due to climate change, geological changes, or burial beneath impermeable formations. These fossil aquifers represent underground water reserves that accumulated over thousands of years during past wet periods, but which are now being depleted by contemporary use at rates that far exceed their natural recharge rates, making them essentially non-renewable water resources. Chemical evolution over geological time creates distinctive signatures in ancient groundwater as water interacts with geological materials during residence times that span thousands or millions of years, allowing for extensive mineral dissolution, precipitation, and chemical reactions that can completely transform the original chemistry of infiltrating water. Ancient groundwater often has much higher dissolved mineral content than young groundwater, reflecting the cumulative effects of long-term water-rock interactions that occur over extended underground residence times. Temperature signatures in ancient groundwater often reflect the ground temperatures that existed when the water first infiltrated, preserving information about past climate conditions in the stable thermal environment of deep underground systems. Ancient groundwater may be significantly warmer or cooler than contemporary groundwater from the same depth, reflecting past climate conditions that were different from contemporary conditions when the ancient water first entered underground systems. Geochemical stratification develops in underground systems where waters of different ages and chemical compositions form distinct layers or zones based on their density, age, and chemical characteristics, creating underground chemical landscapes where different depths or flow paths contain waters with distinctly different properties that reflect their different origins and residence times in underground systems. This stratification can persist for thousands of years in stable underground environments. Noble gas signatures in ancient groundwater preserve information about past atmospheric composition and temperature conditions, as these chemically inert gases dissolved in groundwater reflect the atmospheric conditions that existed when the water was last in contact with the atmosphere. Analysis of noble gas concentrations and ratios can provide detailed information about past air temperatures and atmospheric pressure conditions during ancient recharge periods. Microbial processes in ancient groundwater systems create unique biological environments where specialized microorganisms have adapted to life in water that has been isolated from surface influences for thousands or millions of years, developing metabolic strategies that can utilize the limited energy sources available in deep, ancient groundwater systems. These ancient microbial communities often represent some of the oldest continuous biological systems on Earth. Mixing zones between ancient and modern groundwater create transition areas where waters of dramatically different ages come into contact, leading to chemical reactions and biological processes that affect both water types and create hybrid waters with intermediate ages and chemical characteristics. These mixing zones often occur at aquifer boundaries, fracture intersections, or areas where pumping has altered natural flow patterns and brought different water types into contact. Regional flow systems transport ancient water across entire geological basins through deep underground pathways that connect mountain front recharge areas to discharge areas that may be hundreds of miles away, creating flow systems where water that infiltrated in highland areas emerges in lowland springs after residence times that can span thousands of years. These regional systems demonstrate how ancient recharge can continue to support contemporary discharge long after the original recharge conditions have changed. Overpressured ancient water systems develop where geological processes have compressed ancient groundwater to pressures that exceed normal hydrostatic pressure, creating underground environments where ancient water exists under stress conditions that can drive rapid flow when pressure is released through natural or artificial openings. These overpressured systems often contain very ancient water that has been preserved under pressure for millions of years. Climate change impacts on ancient groundwater include alterations to natural discharge patterns, changes in mixing relationships between ancient and modern water, and modifications to recharge areas that affect the replenishment of aquifer systems that contain ancient water. Contemporary climate change may alter the balance between ancient and modern water in many groundwater systems, potentially affecting water quality and availability in regions that depend on ancient groundwater reserves. Archaeological hydrology uses ancient groundwater to understand past human settlements and activities, as ancient water sources often determine the locations of past civilizations and continue to provide information about the water resources that were available to past human populations. Ancient springs and wells often mark the locations of important historical sites and provide continuity between past and present water use patterns. Hydrochemical fingerprinting of ancient waters creates distinctive chemical signatures that can be used to trace the origins and flow paths of ancient groundwater, identifying connections between different parts of regional flow systems and distinguishing between waters that originated from different recharge sources or time periods. These chemical fingerprints often persist for thousands of years in stable underground environments. Thermal maturation of ancient groundwater occurs as water moves through increasingly deep and warm underground environments over geological timescales, leading to chemical changes that reflect the temperature and pressure conditions encountered during long residence times in deep underground systems. This thermal maturation can create distinctive chemical signatures that indicate the maximum temperatures encountered during underground flow. Ancient discharge systems include springs and seeps that have been flowing continuously for thousands of years, maintaining surface water features and ecosystems that depend on the steady availability of ancient groundwater discharge. These ancient discharge systems often support unique biological communities that have co-evolved with stable groundwater sources over thousands of years, creating ecological refugia that preserve species and communities that might otherwise have been eliminated by climate changes. Resource management of ancient groundwater requires understanding of the non-renewable nature of many ancient water reserves and the need to balance contemporary water use with the preservation of ancient water resources for future needs. Ancient groundwater often represents irreplaceable water reserves that accumulated over thousands of years, but which can be depleted in decades through intensive pumping, making their management a critical issue for long-term water security. Scientific insights from ancient groundwater continue to revolutionize understanding of past climate conditions, groundwater flow systems, and the long-term behavior of underground water systems, providing information about Earth's water cycle that extends far beyond the period of instrumental records and revealing how groundwater systems respond to climate changes over timescales that encompass multiple ice age cycles and major environmental transitions. The presence of ancient water in contemporary groundwater systems creates connections between past and present that demonstrate the long-term persistence and memory of underground water systems, revealing how water that fell as rain during completely different environmental conditions continues to flow through underground systems and influence contemporary water resources, ecosystem function, and human water supplies. This ancient water, flowing silently beneath our feet, represents a direct physical connection to Earth's climatic and environmental history, carrying forward through time the chemical memory of past worlds and past conditions that existed long before human observation and measurement, yet continuing to influence and support the contemporary world through the patient persistence of underground flow that operates on timescales that bridge geological and human perspectives on water resource management and environmental change. Far from being a sterile underground environment of rock and water, the hidden aquifer systems that extend beneath your resting place teem with life forms so specialized and remarkable that they represent some of Earth's most unique biological communities, creating underground ecosystems that operate according to principles completely different from surface ecosystems, yet demonstrate the same complexity, interdependence, and evolutionary creativity that characterizes life wherever it finds opportunities to establish itself and flourish in harmony with available environmental conditions and energy sources. The discovery of extensive life in groundwater systems has revolutionized understanding of Earth's biosphere, revealing that the underground environment supports biological communities that may contain more total biomass than many surface ecosystems, while harboring species diversity that includes countless organisms that have never been described by science and may be found nowhere else on Earth. These underground biological communities demonstrate life's remarkable ability to adapt to environments that lack sunlight, have limited nutrient availability, and operate under physical and chemical conditions that would seem inhospitable to most surface-dwelling organisms. Groundwater microorganisms form the foundation of underground food webs, representing bacterial and archaeal communities that have evolved specialized metabolic strategies for extracting energy from chemical sources available in underground environments rather than from sunlight-based photosynthesis that powers most surface ecosystems. These microorganisms can derive energy from sulfur compounds, iron minerals, methane, hydrogen, and countless other chemical substrates that become available through water-rock interactions in underground systems. Chemosynthetic ecosystems in groundwater environments create biological communities that parallel the deep-sea hydrothermal vent communities that exist in ocean depths, demonstrating how life can create complex ecosystems based entirely on chemical energy rather than solar energy. These chemosynthetic communities often include primary producers that create organic matter from inorganic chemical substrates, supporting food webs that can include multiple trophic levels despite the absence of any photosynthetic energy input. Groundwater invertebrates include specialized animals that have adapted to life in the perpetual darkness and limited space of underground aquatic environments, evolving characteristics like enhanced sensory capabilities, reduced or absent eyes, pale or transparent body coloration, and highly efficient metabolisms that allow them to survive in environments with very limited food availability. These groundwater invertebrates often include endemic species that are found in single aquifer systems or even individual wells, Stygofauna represents the specialized animal communities that inhabit groundwater environments, including crustaceans, worms, insects, and other invertebrates that have evolved specifically for life in underground aquatic environments. Many Stygofauna species are relict populations that represent evolutionary lineages that have been isolated in underground environments for millions of years, preserving ancient genetic characteristics that have been lost in surface populations of related species. Cave-dwelling aquatic communities exist in karst aquifer systems where underground streams and pools support biological communities that include both true aquatic species and terrestrial species that depend on underground water sources for survival. These cave aquatic communities often include fish species that have evolved specialized characteristics for cave life, including enhanced lateral line systems for navigation in darkness and modified feeding strategies for environments with limited food availability. Biofilm communities coat the surfaces of underground rock and sediment materials, creating living layers where microorganisms grow in complex, organized communities that can profoundly affect water chemistry, flow characteristics, and the availability of nutrients for other underground organisms. These biofilms often include multiple species of bacteria and archaea that work together to process nutrients, create favorable chemical conditions, and provide habitat structure for larger underground organisms. Microbial mats develop in areas where groundwater flow creates stable chemical gradients that support layered biological communities with different species occupying different chemical zones based on their metabolic requirements and tolerances. These microbial mats can create striking visual displays of different colored layers representing different microbial communities, while also creating important habitat structure and nutrient processing capabilities for underground ecosystems. Nutrient cycling in groundwater ecosystems involves complex biological and chemical processes where underground organisms break down organic matter, process dissolved nutrients, and create chemical conditions that affect the availability of essential elements for biological communities throughout the underground system. This nutrient cycling often operates much more slowly than surface ecosystem nutrient cycling, but can be equally complex and equally important for maintaining ecosystem function. Groundwater food webs demonstrate ecological relationships that can be surprisingly complex despite the apparent simplicity of underground environments, with energy flowing from chemosynthetic primary producers through multiple levels of consumers that include filter feeders, predators, decomposers, and parasites. These underground food webs often include ecological relationships that have no direct parallels in surface ecosystems due to the unique environmental conditions of underground systems. Endemic groundwater species represent biological treasures that exist nowhere else on Earth, having evolved in isolated underground environments that have allowed for independent evolutionary development over thousands or millions of years. These endemic species often include entire genera or families that are unique to specific aquifer systems, representing irreplaceable biological heritage that can be threatened by changes to groundwater conditions. Adaptation strategies of groundwater organisms include evolutionary modifications that enhance survival in underground environments, such as increased longevity to compensate for low reproductive rates, enhanced efficiency in nutrient utilization to cope with limited food availability, and specialized sensory systems that compensate for the absence of visual cues in permanently dark underground environments. Vertical zonation in groundwater biological communities creates distinct ecological layers where different depths support different communities based on water chemistry, flow characteristics, nutrient availability, and connection to surface influences. Shallow groundwater often supports communities that retain some connection to surface ecosystems, while deep groundwater supports highly specialized communities that are completely independent of surface biological processes. Seasonal patterns in groundwater ecosystems reflect changes in water table elevation, flow patterns, and chemical conditions that affect underground biological communities, creating temporal rhythms in underground ecosystems that may be much more subtle than surface seasonal patterns, but which still create important variations in ecological conditions and biological activity levels throughout underground systems. Symbiotic relationships in groundwater communities include complex partnerships between different species that have co-evolved to create mutually beneficial arrangements that enhance survival in resource-limited underground environments. These symbiotic relationships often involve partnerships between different types of microorganisms that can share metabolic capabilities and create combined metabolic pathways that neither partner could accomplish independently. Contamination impacts on groundwater ecosystems demonstrate how human activities can profoundly affect underground biological communities through changes in water chemistry, introduction of toxic substances, and alteration of natural flow patterns that affect habitat availability and ecological relationships. Groundwater contamination can eliminate endemic species and disrupt ecological processes that may have been stable for thousands of years. Conservation of groundwater ecosystems requires recognition of the unique biological value of underground communities and the development of management strategies that protect both water quality and habitat conditions necessary for maintaining underground biological diversity. This conservation challenge is complicated by the hidden nature of groundwater ecosystems and the limited knowledge that exists about most underground biological communities. Bioremediation applications utilize the natural biological processes of groundwater ecosystems to help clean up contaminated groundwater through enhanced biological activity that can break down pollutants, immobilize toxic metals, and restore natural chemical conditions. These bioremediation approaches take advantage of the specialized metabolic capabilities of groundwater microorganisms to accomplish cleanup goals that would be difficult or impossible to achieve through purely physical or chemical treatment methods. Research techniques for studying groundwater ecosystems include specialized sampling methods, molecular techniques for identifying microorganisms, and experimental approaches that can characterize ecological relationships and biological processes in underground environments that are difficult to access and observe directly. These research approaches continue to reveal new aspects of underground biological diversity and ecosystem function. Climate change impacts on groundwater ecosystems include changes in recharge patterns that affect habitat availability, temperature changes that affect biological communities adapted to stable thermal conditions, and changes in chemical conditions that can affect species survival and ecological relationships. These climate impacts may be particularly significant for endemic groundwater species that have very limited ability to migrate to new habitats. Ecosystem services provided by groundwater biological communities include water purification through biological processing of dissolved substances, maintenance of aquifer permeability through biological processes that prevent clogging, and contributions to regional biodiversity that support scientific research and potential biotechnology applications. These ecosystem services often operate invisibly, but provide important benefits for both groundwater quality and broader environmental health. Evolutionary processes in groundwater environments create opportunities for rapid evolutionary change in isolated underground populations, leading to the development of new species and specialized adaptations that demonstrate evolution's creativity in exploiting new environmental opportunities. These evolutionary processes often operate much faster than would be expected in more stable environments, due to the specialized environmental conditions and isolated populations that characterize many groundwater systems. Ecological restoration of groundwater ecosystems involves efforts to restore natural biological communities in aquifer systems that have been degraded by contamination, overpumping, or other human impacts, using approaches that may include habitat restoration, species reintroduction, and management of factors that affect groundwater ecosystem health. These restoration efforts are often challenging due to the long timescales required for ecosystem recovery in underground environments. International recognition of groundwater biological diversity has led to increased efforts to survey, catalog, and protect underground biological communities around the world, revealing that groundwater ecosystems represent a significant component of global biodiversity that has been largely overlooked by traditional biological surveys and conservation efforts. This international recognition is leading to new research programs and conservation initiatives focused on protecting groundwater biological heritage. The living aquifer systems that exist beneath our feet represent one of Earth's last biological frontiers, harboring communities of organisms that have evolved in isolation for millions of years and which continue to reveal new insights about life's adaptability, ecosystem function, and evolutionary creativity. These underground biological communities demonstrate that life finds ways to flourish even in environments that seem impossibly challenging, creating complex ecosystems that operate according to different principles than surface ecosystems, but which exhibit the same fundamental characteristics of biological creativity, ecological interdependence, and evolutionary adaptation that characterize life wherever it establishes itself in harmony with available environmental opportunities and energy sources. Where the hidden underground rivers that flow beneath your feet finally return to the surface world, they create some of Earth's most magical and life-giving features. The springs and seeps that serve as windows into the underground realm, revealing glimpses of the vast water systems that exist below ground, while creating surface oases that support unique ecosystems and provide reliable water sources that have sustained life for millions of years. These emergence points represent the culmination of underground journeys that may have begun hundreds of miles away and decades or centuries ago, bringing to the surface water that carries with it the chemical memory of its underground travels and the biological communities that depend on the stable conditions that underground water sources provide. Spring formation occurs where underground water encounters geological conditions that force its emergence at the surface, creating natural outlets where the pressure, permeability, and topographic conditions combine to bring underground flow back into the realm of sunshine and surface weather. These emergence points can range from barely visible seeps, where water slowly emerges through soil or rock, to dramatic artesian springs where pressurized underground water erupts from the ground with considerable force, creating instant streams or pools that appear to emerge from solid rock. Artesian springs represent the most dramatic form of groundwater emergence, where water confined in underground systems under pressure finds pathways to the surface and flows upward, driven by the hydraulic head that is built up during the water's journey through pressurized underground systems. These artesian conditions can create springs that flow continuously for thousands of years, maintaining constant flow rates and temperatures that reflect the stable conditions of the deep underground systems that feed them. Spring zones often develop where multiple groundwater discharge points cluster together, creating areas where numerous springs and seeps emerge within relatively small geographic areas due to favorable geological conditions that promote groundwater discharge. These spring zones can create unique ecological environments where the influence of stable groundwater discharge creates microclimates and habitat conditions that support plant and animal communities that differ dramatically from surrounding areas that depend on variable surface water sources. Thermal springs emerge where groundwater has been heated during its underground journey through contact with geothermal heat sources or simply through the normal increase in temperature that occurs with depth in the Earth's crust. These thermal springs can range from slightly warm to extremely hot, creating surface features that demonstrate the thermal energy that exists in underground systems and providing habitat for specialized thermophilic organisms that have adapted to elevated temperature conditions. Cold springs represent the more common form of groundwater emergence, where underground water reaches the surface with temperatures that reflect the stable thermal conditions of shallow to moderate depth underground systems. These cold springs typically have temperatures that approximate the mean annual air temperature of their recharge areas, providing remarkably stable thermal conditions that create important refugia for temperature-sensitive organisms during extreme weather periods. Seasonal springs demonstrate the dynamic relationship between underground water systems and surface hydrological conditions, emerging during periods when groundwater levels are high and ceasing to flow when underground water levels drop below the elevation of their emergence points. These seasonal springs create temporary surface water features that can be crucial for wildlife during specific seasons while demonstrating the fluctuating nature of groundwater surface water interactions. Perennial springs maintain continuous flow throughout all seasons and weather conditions, fed by underground water systems that are sufficiently large and stable to provide reliable discharge regardless of short-term variations in recharge or climatic conditions. These perennial springs often serve as critical water sources for both wildlife and human communities, providing water security that transcends the variability of surface water supplies. Spring ecosystems create unique biological communities that combine aquatic and terrestrial elements in ways that are determined by the specific characteristics of groundwater emergence, including flow rate, temperature, chemical composition, and seasonal variability. These spring ecosystems often support endemic species that have evolved specifically to exploit the unique environmental conditions created by the interface between underground and surface water systems. Chemical signatures of springs reflect the geological formations and underground flow paths that the water has encountered during its subsurface journey, creating distinctive water chemistry that can serve as a fingerprint identifying the source and history of underground flow systems. These chemical signatures often include elevated concentrations of dissolved minerals that reflect specific rock types, along with temperature and gas content that provide information about the depth and pathways of underground circulation. Seepage areas represent more diffuse forms of groundwater discharge, where underground water emerges gradually over broader areas rather than at discrete spring points, creating wetland conditions that may extend across considerable areas while being fed by distributed groundwater discharge that occurs through less permeable surface materials. These seepage areas often create some of the most productive and biologically diverse ecosystems in landscapes that are otherwise water-limited. Gaining streams receive water from groundwater discharge along their channels, demonstrating how underground river systems contribute to surface stream flow through distributed discharge that occurs along stream banks and channel bottoms. This groundwater contribution often provides the base flow that maintains stream flow during dry periods when surface runoff is minimal, revealing the critical importance of underground water systems for maintaining surface aquatic ecosystems. Spring-fed lakes and ponds are created where groundwater discharge occurs in topographic depressions that allow discharged water to accumulate rather than flowing away as streams, creating permanent or semi-permanent water bodies that are fed by the reliable flow of underground water sources. These spring-fed water bodies often have distinctive ecological characteristics that reflect the stable water supply and unique chemistry of their groundwater sources. Oasis ecosystems in arid regions depend almost entirely on groundwater discharge through springs and seeps, creating islands of biological productivity and diversity in landscapes that would otherwise be too dry to support complex plant and animal communities. These groundwater-dependent ecosystems demonstrate the critical importance of underground water systems for maintaining biological diversity and ecosystem function in water-limited environments. Cultural significance of springs extends throughout human history, as reliable groundwater sources have served as focal points for human settlement, religious significance, and cultural identity for countless societies that have recognized springs as life-giving features that connect the surface world to mysterious underground realms. Many springs have been considered sacred sites that represent connections between the physical and spiritual worlds. Hydrogeological processes that create springs involve complex interactions between underground flow systems, geological structures, and topographic features that create the specific conditions necessary for groundwater emergence. Understanding these processes requires appreciation of three-dimensional groundwater flow patterns, the influence of geological heterogeneity on flow paths, and the dynamic relationships between recharge and discharge areas that may be separated by considerable distances. Spring discharge rates can vary dramatically both between different springs and within individual springs over time, reflecting variations in underground flow systems, seasonal recharge patterns, and longer-term changes in groundwater conditions. Some springs maintain remarkably constant discharge rates that vary by only small percentages over many years, while others show dramatic seasonal or longer-term variations that reflect the characteristics of their underground source systems. Capture zones of springs represent the underground watersheds that contribute water to specific spring systems, defining the geographic areas where precipitation and surface water infiltration will eventually emerge at particular springs after traveling through underground flow systems. These capture zones can be much larger than surface watersheds and may extend across multiple surface drainage basins, demonstrating the complex relationship between surface and underground water systems. Restoration of degraded springs involves efforts to restore natural flow patterns, water quality, and ecological conditions in spring systems that have been affected by human activities, including groundwater pumping, land use changes, and contamination sources. Spring restoration often requires management of activities throughout the entire capture zone that contributes water to the spring system, demonstrating the landscape-scale connections that characterize groundwater-dependent ecosystems. Climate change impacts on springs include alterations to recharge patterns that affect spring discharge rates, temperature changes that affect spring ecology, and shifts in precipitation patterns that can affect the long-term sustainability of groundwater sources that feed spring systems. These climate impacts can be particularly significant for springs that depend on recharge from mountain snowpack or other precipitation sources that are sensitive to changing climate conditions. Monitoring of spring systems provides important information about the condition and trends of underground water systems, as springs serve as natural monitoring points where changes in underground flow, water quality, and ecological conditions become visible at the surface. Long-term monitoring of spring discharge, temperature, and chemistry can reveal trends in groundwater systems that would be difficult to detect through other monitoring approaches. Conservation strategies for spring-dependent ecosystems require protection of both the immediate spring area and the broader groundwater systems that feed spring discharge, including management of land use activities throughout spring capture zones and protection of recharge areas that may be located far from the spring emergence points. These conservation efforts often require coordination across multiple jurisdictions and land ownerships that may be connected by underground flow systems. Economic values of springs include their importance as water sources for human use, their role in supporting tourism and recreation activities, their contribution to agricultural productivity in arid regions, and their value as indicators of groundwater resource availability. These economic values often extend far beyond the immediate spring locations to include broader economic benefits that result from the reliable water supplies and unique ecosystems that springs support. Research applications using springs include studies of groundwater flow systems, climate change impacts on water resources, ecological relationships in groundwater-dependent ecosystems, and biogeochemical processes that occur at the interface between underground and surface water systems. Springs provide natural laboratories where researchers can study processes that would be difficult to investigate in other settings. Global distribution of springs reflects the worldwide occurrence of geological and hydrological conditions that promote groundwater discharge, creating spring-dependent ecosystems in virtually every climate zone and geographical region on Earth. This global distribution demonstrates the universal importance of groundwater systems and the widespread occurrence of the geological conditions that create opportunities for underground water to return to the surface world. Traditional knowledge about springs includes indigenous and local understanding of spring behavior, seasonal patterns, and ecological relationships that has been developed through generations of observation and dependence on spring water sources. This traditional knowledge often provides insights into long-term spring behavior and ecological relationships that complement scientific understanding and contribute to effective spring management and conservation. Future challenges for spring conservation include increasing demands for groundwater resources, climate change impacts on recharge patterns, land use changes that affect spring capture zones, and the need for improved understanding of the complex relationships between underground flow systems and spring discharge patterns. Meeting these challenges will require integration of scientific research, traditional knowledge, and innovative management approaches that recognize the connections between springs and the larger groundwater systems that sustain them. The emergence of underground rivers at springs and seeps creates magical transitions where the hidden water world becomes visible, demonstrating the continuous circulation that connects all parts of the hydrological cycle, while providing essential habitat and water resources that support both natural ecosystems and human communities. These emergence points serve as reminders of the vast underground water systems that exist beneath our feet, bringing to the surface the gifts of water that has traveled long distances and long times through the patient circulation of underground rivers that connect distant places and different times through the persistent flow of water that eventually finds its way back to the light. Stretching across continents beneath the solid ground where you rest lies a vast network of underground highways where water travels distances that can span entire geographic regions. Following pathways through geological formations that create transportation corridors more extensive than any surface highway system. Carrying water from mountain recharge areas to distant coastal discharge zones through underground routes that may extend for hundreds or even thousands of miles while maintaining organized flow patterns that demonstrate how underground systems can achieve remarkable feats of long-distance water transport. Regional groundwater flow systems represent some of the most impressive examples of long-distance underground water transport, creating flow paths that can extend from continental divides to ocean coastlines while maintaining hydraulic continuity across multiple geological formations and geographic provinces. These regional systems demonstrate how underground water can travel distances that dwarf most surface river systems while maintaining organized flow patterns that connect geographically distant areas through hidden underground pathways that operate according to hydraulic principles that can overcome topographic barriers that would block surface water flow. Continental-scale aquifer systems create underground highways that can span entire continents, transporting water across geological basins that may encompass multiple countries and climate zones, while maintaining flow continuity through sequences of interconnected permeable formations that allow water to travel from recharge areas in one geographic region to discharge areas in completely different geographic and climatic settings. These continental systems demonstrate the truly massive scale on which underground water transport can operate. Paleochannel systems represent ancient underground highways where buried river valleys continue to serve as preferential pathways for groundwater flow long after the surface rivers that created them have been covered by later geological deposits or diverted to different courses. These buried river systems often represent the most permeable and well-connected flow paths in regional groundwater systems, concentrating underground flow along routes that preserve the drainage patterns of ancient surface landscapes that may have existed millions of years ago. Cross-formational flow describes how underground water can move between different geological formations through fracture systems, unconformities, and other geological features that create vertical connections between otherwise separate aquifer systems. These cross-formational connections create three-dimensional flow networks that allow water to move not just horizontally across large distances, but also vertically between different geological layers, creating complex flow patterns that could transport water through multiple aquifer systems during a single underground journey. Hydraulic conductivity contrasts between different geological formations create underground highways, where highly permeable formations serve as preferential flow paths that can transport water much more efficiently than surrounding, less permeable materials. These conductivity contrasts can create underground flow patterns where most of the water movement is concentrated in relatively narrow zones of high permeability, while extensive areas of low permeability serve primarily as storage zones that release water slowly to the high conductivity flow paths. Fracture networks in consolidated rock create underground highway systems where water movement is concentrated along interconnected fracture systems that may extend for many miles through otherwise relatively impermeable rock formations. These fracture networks can create highly anisotropic flow systems where water moves much more easily in certain directions than in others, depending on the orientation and connectivity of the fracture patterns that control underground flow paths. Inter-basin groundwater transfer occurs where underground flow systems cross surface watershed divides, creating hidden connections between surface river basins that appear to be completely separate from surface perspectives, but which are connected through underground flow paths that can transfer water from one surface watershed to another. These inter-basin transfers demonstrate how underground flow systems can create hydrological connections that are completely invisible from surface observations. Groundwater age gradients along underground highways provide evidence of the timescales involved in long-distance underground water transport, with water age typically increasing with distance from recharge areas and revealing residence times that can span decades, centuries, or even millennia for water that travels the full length of major underground highway systems. These age gradients demonstrate the patient timescales on which underground water transport operates. Chemical evolution along flow paths creates distinctive signatures that reflect the cumulative effects of water-rock interactions during long-distance underground transport, with water chemistry becoming progressively more mineralized and chemically distinct as water moves along underground highways and encounters different geological formations that contribute their own chemical signatures to the traveling water. This chemical evolution creates a kind of chemical memory that preserves information about the underground journey. Flow velocity variations within underground highway systems create situations where different portions of the flow move at dramatically different speeds, with some water traveling relatively quickly through high permeability zones, while other water moves much more slowly through lower permeability portions of the same flow system. These velocity variations can create complex mixing patterns and age distributions that reflect the heterogeneous nature of underground flow paths. Pressure transmission along underground highways allows changes in hydraulic conditions in one part of a regional flow system to influence water levels and flow patterns hundreds of miles away, creating long-distance connections where events like changes in pumping patterns or recharge conditions can have effects that propagate along underground flow paths and influence groundwater conditions in distant areas that may be located in completely different geographic and political jurisdictions. Transboundary groundwater flow creates underground highways that cross international borders, creating shared water resources that require coordinated management between different countries that may have very different approaches to water resource development and environmental protection. These transboundary underground systems demonstrate how underground water transport can create resource management challenges that transcend political boundaries and require international cooperation. Deep circulation systems represent the most extensive underground highways, where water can circulate through deep geological formations over distances that span continents, while following flow paths that may extend thousands of feet below the surface through geological formations that have been largely isolated from surface influences for millions of years. These deep systems often transport water that originally infiltrated in mountain regions and emerges in lowland areas after underground journeys that can span geological timescales. Geothermal transport along underground highways occurs where deep circulation systems encounter elevated temperatures due to geothermal heat sources, creating opportunities for heat transport that can affect surface temperature patterns and create thermal anomalies that reveal the presence of deep underground flow systems. These geothermal effects can create surface features like warm springs and geothermal areas that reflect the influence of deep underground circulation. Storage and transmission along underground highways involves the complex relationship between water storage and aquifer systems and the transmission of water through those same systems over long distances. Underground highway systems must balance the competing demands of providing long-term water storage and maintaining flow continuity over great distances, creating systems that can serve both storage and transport functions simultaneously. Aquitard systems create barriers and controls within underground highway networks, where low permeability formations can redirect underground flow, create pressure compartments, and influence the efficiency of long-distance water transport. These aquitard systems often determine the specific pathways that underground highways follow and can create complex flow patterns where water must find circuitous routes around geological barriers. Pumping impacts on underground highways demonstrate how human activities can influence flow patterns in regional groundwater systems, with large-scale groundwater extraction creating cones of depression that can redirect underground flow paths and potentially capture water that would naturally discharge at distant locations. These pumping impacts can affect the functioning of underground highway systems over distances of hundreds of miles from the actual pumping locations. Climate change effects on underground highways include alterations to recharge patterns that affect the source areas for long-distance underground flow, changes in discharge patterns that affect the destinations of underground transport, and potential changes in the efficiency of underground transport due to changing temperature and precipitation patterns that affect the hydrogeological conditions that control underground flow. Contamination transport along underground highways creates environmental challenges where contaminants that enter groundwater systems can be transported over great distances through underground flow paths, potentially affecting water quality in areas that are hundreds of miles from the original contamination sources. This long-distance contamination transport demonstrates both the connectivity of underground systems and the potential for local contamination to have regional impacts. Isotopic tracers reveal the pathways and timescales of underground highway systems by providing chemical signatures that can track the movement of water through underground flow systems and reveal connections between recharge and discharge areas that may be separated by great distances. These isotopic techniques have revolutionized understanding of regional groundwater systems and revealed the extent and complexity of underground highway networks. Modeling of underground highway systems requires sophisticated computational approaches that can simulate flow patterns across multiple geological formations over distances that span entire continents. Incorporating complex geological heterogeneity, variable boundary conditions, and three-dimensional flow patterns that reflect the true complexity of regional groundwater systems. These modeling efforts continue to reveal new insights about the functioning of underground highway networks. Economic significance of underground highway systems includes their importance for regional water supply, their role in supporting agricultural development in arid regions, and their potential for providing water security that transcends local water availability. These underground highways often represent critical infrastructure that supports economic development and population centers across entire geographic regions. Ecological connections created by underground highways include the support of discharge-dependent ecosystems that may be located hundreds of miles from their ultimate water sources, creating ecological relationships that span entire continents through underground flow connections. These ecological connections demonstrate how underground systems create biological relationships that transcend surface geographic boundaries. Conservation challenges for underground highway systems include the need for coordinated management across multiple jurisdictions, the difficulty of monitoring systems that span such large geographic areas, and the complexity of balancing competing demands for water resources that may serve multiple purposes along their underground transport routes. These conservation challenges require innovative approaches that recognize the regional scale of underground highway systems. Technological advances in studying underground highways include improved geophysical techniques for mapping subsurface geology, advanced chemical analysis methods for tracking water movement, and sophisticated modeling approaches that can simulate complex flow patterns across multiple scales. These technological advances continue to reveal new aspects of underground highway systems and improve understanding of their functioning and management requirements. International cooperation in managing underground highway systems has led to the development of transboundary agreements, shared monitoring programs, and coordinated research efforts that recognize the international scope of many underground flow systems. This cooperation demonstrates how underground highways create shared interests that can promote collaboration between countries that share groundwater resources. Future challenges for underground highway systems include increasing demands for groundwater resources, climate change impacts on flow patterns, the need for improved monitoring and management approaches, and the challenge of maintaining the long-term sustainability of systems that operate on timescales that span multiple human generations. Meeting these challenges will require continued advances in scientific understanding, management techniques, and international cooperation. The underground highways that exist beneath our feet represent one of Earth's most remarkable transportation systems, moving water across distances that span continents, while maintaining organized flow patterns that connect distant geographic regions through hidden pathways that operate with patient persistence over timescales that dwarf human experience. These underground transportation networks demonstrate the interconnected nature of Earth's water systems and reveal how water that infiltrates in one location can support ecosystems and human communities thousands of miles away through the quiet efficiency of underground flow that creates connections across vast distances through the steady persistence of hydraulic gradients that drive water through the complex three-dimensional pathways that comprise Earth's hidden network of underground highways. In the most profound depths beneath where you rest, far below the familiar underground systems that interact with surface weather and seasonal changes, there exists a realm of water circulation so deep and ancient that it operates according to principles that blend hydrology with geology in ways that create underground water systems of extraordinary scale and complexity. These deep circulation systems extend thousands of feet below the surface, reaching depths where underground water encounters temperatures, pressures, and geological conditions that transform both the water and the rock through which it moves, creating chemical and physical processes that operate on timescales measured in thousands or millions of years. Deep groundwater systems begin where conventional groundwater circulation gives way to increasingly extreme conditions that reflect the growing influence of geothermal heat, lithostatic pressure, and geological processes that operate far beneath the influence of surface environmental conditions. At these depths, water movement becomes dominated by density differences created by temperature variations, pressure gradients that reflect deep geological structures, and chemical processes that can fundamentally alter both water chemistry and rock properties through long-term water-rock interactions that occur under conditions of elevated temperature and pressure. Geothermal circulation represents one of the most dramatic forms of deep water movement, where underground water encounters heat sources that can raise water temperatures to levels that approach or exceed the boiling point of water at surface pressures. This geothermal heating creates convection currents that can drive vigorous circulation of underground water over vertical distances that span thousands of feet, transporting both water and heat through deep underground systems that can influence surface conditions hundreds of miles from their deep underground origins. Hydrothermal systems develop where deep circulation encounters particularly intense heat sources, creating underground environments where superheated water can dissolve minerals at rates that far exceed normal groundwater processes, creating unique underground chemical environments where new minerals can precipitate, existing rocks can be dramatically altered, and water chemistry can evolve to compositions that are completely different from shallow groundwater. These hydrothermal processes often create distinctive rock formations and mineral deposits that preserve evidence of past deep circulation events. Metamorphic water represents water that has been so profoundly altered by deep circulation processes that its original identity as meteoric water may be completely obscured by the chemical and isotopic changes that occur during residence times of thousands or millions of years in deep underground systems. This metamorphic water often has chemical compositions that reflect the high temperature, high-pressure conditions of deep circulation systems and may preserve evidence of geological processes that occurred deep within the Earth's crust. Deep crustal fluids include waters that circulate through the deepest accessible parts of the Earth's crust, reaching depths where temperatures may exceed several hundred degrees and pressures may reach levels that are thousands of times greater than atmospheric pressure. These deep crustal fluids often play important roles in geological processes, including mineral formation, rock alteration, and the transport of chemical elements through deep crustal systems that operate on geological timescales. Convective circulation in deep systems occurs where temperature and density gradients create buoyancy forces that can drive vigorous water movement through deep underground systems, creating circulation patterns that can transport water vertically through thousands of feet of rock, while also creating horizontal flow patterns that can extend for many miles through deep geological formations. These convective systems often create complex, three-dimensional flow patterns that can be much more vigorous than the gravity-driven flow that characterizes shallow groundwater systems. Pressure-driven flow in deep systems reflects the influence of lithostatic pressure that increases dramatically with depth, creating pressure gradients that can drive water movement through deep rock formations even when temperature effects are minimal. These pressure-driven systems often create opportunities for water to move through rock formations that would be essentially impermeable under surface pressure conditions, demonstrating how extreme pressure can fundamentally alter the hydraulic properties of geological materials. Chemical reactions between water and rock reach extraordinary intensity in deep circulation systems, where elevated temperatures and pressures greatly accelerate reaction rates and allow for chemical processes that cannot occur under surface conditions. These deep chemical reactions can create entirely new mineral assemblages, alter the physical properties of rock formations, and generate chemical byproducts that can be transported to surface environments through deep circulation pathways. Mineral dissolution and precipitation in deep systems occur at rates and with products that are impossible under surface conditions, creating opportunities for the formation of valuable mineral deposits and the development of unique rock formations that preserve evidence of past deep circulation events. The mineral products of deep circulation often include economically important deposits of metals, nonmetals, and energy resources that represent concentrated products of deep underground chemical processes. Deep thermal anomalies develop where deep circulation systems transport heat from great depths toward the surface, creating temperature patterns that can influence surface geological processes and create distinctive surface features, including hot springs, geysers, and geothermal fields that reveal the presence of deep circulation systems. These thermal anomalies often extend for considerable distances around deep circulation systems and can influence regional climate patterns through their effects on surface temperature conditions. Isotopic signatures of deep circulation water often show distinctive patterns that reflect the extreme conditions and long residence times that characterize deep underground systems, with isotopic compositions that can provide information about the temperature, pressure, and chemical conditions encountered during deep circulation. These isotopic signatures often preserve evidence of deep circulation processes that occurred thousands or millions of years ago and continue to influence contemporary deep groundwater chemistry. Carbon cycling in deep systems involves complex processes where carbon compounds can be transported from surface sources to great depths through deep circulation, undergo chemical transformations under extreme conditions, and potentially return to surface environments carrying carbon in new chemical forms. These deep carbon cycling processes may play important roles in global carbon budgets and long-term climate regulation through their effects on atmospheric carbon dioxide concentrations. Microbial life in deep circulation systems has been discovered at depths and under conditions that were previously thought to be incompatible with life, revealing that specialized microorganisms have adapted to survive and thrive in the extreme temperature, pressure, and chemical conditions that characterize the deepest groundwater circulation systems. These deep microbial communities often represent some of the most extreme life forms on Earth and may provide insights into the origins of life and the potential for life in extreme environments elsewhere in the solar system. Seismic influences on deep circulation include the effects of earthquakes and tectonic processes on deep groundwater flow patterns, with seismic activity potentially opening new flow pathways, altering pressure conditions, and influencing the connectivity of deep circulation systems. These seismic effects can create opportunities for deep waters to reach surface environments through pathways that may be opened or enhanced by tectonic activity. Volcanic connections to deep circulation systems often involve the interaction between deep groundwater and magmatic processes, with deep circulation potentially providing water that can influence volcanic activity, while volcanic heat sources can drive deep circulation processes. These volcano-groundwater interactions can create complex feedback relationships that influence both hydrological and geological processes over regional scales. Economic resources associated with deep circulation include geothermal energy that can be extracted from deep thermal systems, mineral deposits that are formed by deep circulation processes, and deep groundwater resources that may provide water supplies for specialized applications. The economic potential of deep circulation systems continues to be explored through advances in deep drilling technology and improved understanding of deep underground processes. Environmental impacts of deep circulation can include the transport of contaminants to great depths, the influence of deep circulation on surface water quality through deep discharge processes, and the potential for human activities to affect deep circulation systems through deep injection of wastes or extraction of deep resources. Understanding these environmental impacts requires appreciation of the connections between surface activities and deep underground processes. Climate connections to deep circulation involve the potential for deep circulation systems to influence regional and global climate patterns through their effects on surface heat flow, their role in long-term carbon cycling, and their influence on surface water resources that may be affected by deep discharge patterns. These climate connections operate on timescales that span geological periods and may be important for understanding long-term climate stability. Research techniques for studying deep circulation include advanced drilling methods that can reach extreme depths, sophisticated chemical analysis techniques that can characterize deep waters, and geophysical methods that can map deep underground structure and temperature patterns. These research approaches continue to reveal new aspects of deep circulation systems and improve understanding of their role in Earth system processes. Modeling of deep circulation systems requires computational approaches that can simulate flow patterns under extreme conditions, incorporate complex chemical reaction networks, and account for the influence of temperature, pressure, and geological heterogeneity on deep underground flow patterns. These modeling efforts are essential for understanding and predicting the behavior of deep circulation systems and their interactions with surface environments. Future research directions in deep circulation include efforts to understand the role of deep systems in global elemental cycles, the potential for deep circulation to influence climate regulation, the possibility of extracting energy and resources from deep systems, and the implications of deep circulation for understanding the deep biosphere and the potential for life in extreme environments throughout the solar system. Conservation considerations for deep circulation systems include the need to protect deep groundwater resources from contamination, the importance of maintaining the integrity of deep circulation pathways, and the challenge of managing human activities that may affect deep underground systems. These conservation efforts require long-term perspectives that recognize the extremely slow timescales on which deep circulation systems operate and recover from disturbances. The deep circulation systems that operate thousands of feet beneath the surface represent some of Earth's most extreme and fascinating hydrological processes, creating underground environments where water, heat, and rock interact under conditions that can fundamentally transform all three components through chemical and physical processes that operate on geological timescales. These deep systems demonstrate how water circulation extends throughout the accessible portions of Earth's crust, creating connections between surface environments and deep crustal processes that influence everything from surface spring chemistry to regional geothermal patterns, while supporting forms of life that push the boundaries of what conditions can support biological processes and providing resources and energy sources that may become increasingly important for human society seeking sustainable alternatives to surface-based resources. Resting here in the gentle embrace of evening, surrounded by the quiet presence of the solid earth that supports you, you have traveled through the hidden realm of underground rivers and discovered a world of flowing water that extends infinitely in all directions beneath your feet, revealing itself as one of the planet's most fundamental and persistent processes. The endless circulation of water through underground pathways that connect every raindrop to every spring, every mountain to every ocean, every moment in time to every other moment through the patient persistence of flow that has been continuing for billions of years and will continue for billions more. The water that flows beneath you at this very moment carries within itself the memory of every place it has been, every rock it has touched, every living thing it has sustained during its countless journeys through the underground realm that extend from the shallow soil layers just beneath the surface to the deepest circulation systems that reach toward the Earth's molten interior. This water has been rain and snow, rivers and lakes, clouds and oceans, moving through an endless cycle that connects all water everywhere through the continuous circulation that makes life possible on our remarkable planet. The underground rivers you have explored through our gentle journey together represent more than scientific curiosities or engineering challenges. They embody fundamental principles of connection, persistence, and the quiet power of gradual change that characterizes all of nature's most essential processes. Like the slow breathing that sustains your body during peaceful sleep, like the patient growth that transforms seeds into forests, like the gentle erosion that shapes mountains into valleys, the underground flow of water demonstrates how persistent, quiet action can accomplish transformations that seem impossible when viewed from the perspective of human timescales. In the shallow soil beneath you, water continues its patient percolation through networks of pore spaces and root channels, beginning journeys that may lead to springs that emerge miles away or decades in the future. This water moves with the same quiet determination that it has always shown, following pathways that respect the laws of physics, while somehow finding ways to support every form of life that depends on its presence, creating the foundation for ecosystems and human communities that might never suspect the complexity of the underground world that sustains them. In the deeper aquifers that extend hundreds of feet below, ancient waters continue their slow migration toward distant discharge points, carrying with them the chemical signatures of the rocks they have encountered and the climates they remember from past geological periods when the world was different, but water flowed according to the same fundamental principles that govern its movement today. These ancient waters remind us that the underground realm operates on timescales that dwarf human experience, while providing essential connections between past and present that make possible the remarkable stability of Earth's water cycle. In the deepest circulation systems that reach toward the Earth's interior, water undergoes transformations that connect the hydrological cycle to geological processes, demonstrating how the flow of water participates in the fundamental workings of our planet and contributes to processes that maintain the conditions necessary for life. These deep systems reveal how underground rivers participate in the grand circulation that includes not just water movement, but also the transport of heat, chemicals, and energy that keep our planet dynamic and habitable. The endless flow of underground rivers creates patterns that connect every location on Earth's surface to every other location through pathways that may be direct and rapid or indirect and slow, but which always maintain the essential connections that allow water to find its way from areas of abundance to areas of need. This connectivity demonstrates one of nature's most beautiful principles, that everything is connected to everything else through networks of relationship that ensure the continuation of life even under changing conditions. The biological communities that thrive in underground rivers prove that life finds ways to flourish wherever water flows, adapting to conditions that range from the familiar environments of shallow groundwater to the extreme conditions of deep circulation systems. These underground ecosystems remind us that life is remarkably creative and persistent, finding opportunities for growth and reproduction in environments that might seem impossibly challenging, while contributing to the health and function of the underground systems that support surface life. The springs and seeps where underground rivers return to the surface world create magical connections between the hidden and visible realms of water circulation, bringing to the surface the gifts of water that has been purified, mineralized, and transformed by its journey through underground systems. These emergence points remind us that the underground world is not separate from surface life, but rather provides essential support that makes possible the abundance and diversity of surface ecosystems. The chemical evolution that occurs as water moves through underground systems demonstrates how patient interaction between water and rock creates the mineral content that makes water suitable for supporting life, while also creating the dissolved substances that feed underground ecosystems and contribute to soil fertility when underground water emerges at the surface. This chemical evolution shows how underground rivers serve not just as transportation systems, but also as processing facilities that improve water quality through natural filtration and mineral addition. The thermal stability of underground water systems creates refugia that provide consistent environmental conditions for both biological communities and water supplies, buffering the effects of surface climate variability and providing reliable resources that can sustain life during periods when surface water sources may be limited or highly variable. This thermal stability demonstrates how underground systems provide essential insurance against environmental uncertainty. The underground rivers that flow beneath your feet will continue their endless circulation long after tonight's peaceful rest has ended, carrying forward the ancient patterns of flow that have sustained life on Earth throughout its history, while adapting to changing conditions in ways that demonstrate nature's remarkable resilience and creativity. Tomorrow morning, when you wake and step on a solid ground, you will be supported by the same flowing foundation that has supported countless generations before you and will support countless generations to come. The quiet persistence of underground flow offers lessons about patience, determination, and the power of consistent action over time. Like water finding its way through the smallest openings in rock, persistent effort guided by natural principles can overcome obstacles that seem insurmountable, while the gentle nature of water's action shows how transformation can be accomplished without force or violence, through the patient application of gentle pressure over sufficient time. The connections created by underground rivers remind us that we are never truly isolated, that the water we use and the land we inhabit are connected through underground pathways to distant places and other communities, creating responsibilities and opportunities for cooperation that transcend visible boundaries. The water that emerges from your tap may have begun its journey in mountains hundreds of miles away, while the water that infiltrates in your area may eventually support ecosystems or communities in distant locations. The timescales on which underground rivers operate invite us to consider perspectives that extend beyond immediate concerns to encompass the patient working of natural systems that maintain the conditions necessary for life over periods that span multiple human generations. These long-term perspectives remind us that our current choices about water use and land management will influence underground systems for decades or centuries to come, while the underground water that we use today represents the accumulated gifts of past precipitation and past management decisions. Underground rivers teach us about the hidden support systems that make life possible, reminding us that much of what sustains us operates quietly and invisibly, requiring no recognition or appreciation to continue its essential work. Like the underground rivers that flow unseen beneath our feet, many of the most important aspects of life work best when they operate without fanfare or attention, providing reliable support that can be depended upon precisely because it operates according to consistent principles rather than changing fashions or temporary enthusiasms. The endless flow of water through underground systems demonstrates the possibility of processes that are both dynamic and stable, constantly moving yet reliably persistent, always changing yet fundamentally consistent. This paradox of movement and stability offers insights into how complex systems can maintain themselves over long periods while remaining responsive to changing conditions, providing models for sustainability that honor both continuity and adaptation. Rest now in the knowledge that beneath you flows an endless circulation of water that connects your resting place to the entire planet through pathways of flow that have been operating since long before human civilization began and will continue long after current human concerns have been resolved through the patient working of time and the persistent creativity of natural systems. Let the quiet sound of underground flow that you now understand surrounds you carry you into peaceful sleep, knowing that you rest supported by one of Earth's most fundamental and reliable processes, cradled by the gentle persistence of water that never stops moving, never stops connecting, never stops supporting the endless creativity and remarkable resilience of life on our beautiful planet. The underground rivers flow on through the night, carrying their ancient wisdom through pathways of stone and soil, connecting mountain to sea, past to future, drop to ocean, in the endless circulation that makes all life possible and sustains the remarkable world in which we have the privilege to rest, to wonder, and to find peace in the gentle embrace of flowing water that supports us always, flowing beneath our feet with the patient persistence of love itself, endless and eternal and forever, flowing toward the light.